Okay, hello again, and let's see if my screen is online. Yeah, and here I am. Okay, let's see if this is broadcasting now. And let's wait for confirmation that I am online. Okay, I think I am back, and let's start. So, yeah. So, I was explaining what is Brainfuck. It's a very easy programming language, just 8 commands, just one memory of bytes. We have a position on it. We can move it to the right, to the left. We can increment the byte with overflow. We can decrement the byte with overflow. We can output it somewhere else. We can output it, and we can read a byte, and we can loop. And yeah, so a long time ago, I started reading this series of blog posts, and it progressively is more complex and complex. So Eli starts with a very simple interpreter in C++, and then he measures the time that it takes, and there is a take two. There are some optimizations that can be done to the interpreter, and there is a very well optimized interpreter with take 3 and 4, and I rewrote that in Rust. Let me connect to my Intel machine. Yep. And yeah, so here they are. And if I run, if I compile the Brainfuck interpreter of version 3 and run it with some program like hello BF, and let's look at the program itself. Yeah, I'm not claiming I understand this, but yeah. So, and there is another interesting thing that takes a lot of time, and it draws it prints some approximation of a Mandelbrot fractal. And if I run it, it takes quite a bit of time. So it started fast, but it will be slower to the center. But yeah, it's very impressive that somebody actually had the time to write this in Brainfuck, and it works somehow. But yeah, we will be using this this timing for comparison with the JIT interpreter. Yeah, it's taken quite a bit of time. Now it's much faster, and this is an Intel machine that I'm on right now, and the third version takes 34 seconds, and then I rewrote it into a simple JIT which basically looks like, where is it exactly? Here. So the language is condensed to this. There are no there are no increment operations anymore. There is just and decrement operations. There is add, which compresses sequences of increments and decrements and can take a negative number. And there is a move, which is again compressed, so you don't have a few sequential moves anymore. You just have move by this offset. You have print, you have read, you have begin of the loop and end of the loop. And they, what was that use size? I don't remember exactly, but yeah, that's what it is. So, and compilation looks very, very, very crude. So, first of all, so I basically write machine code into memory, which sets up a new subroutine, a new stack frame. It uses, so it takes in RDI, it takes a what? The address of the memory. So it's an RBP on Intel. And then we clear RBX, which was that the data pointer, I believe. Yeah, and then it just emits sequences of bytes that correspond to machine code. So when we want to change the current cell, we just take RBP as the address of the memory, and we take RBX as an address on it, and then we add the given number to this byte in memory. When we want to move, we just move RBX, and I don't do any bound checking, nothing. So basically, yeah, it's pretty bad that you can go off the rails with this, and yeah, it's basically very unsafe. Okay, so print reads the byte at the current position into AL. 0 extends it, puts it in RDI. The register that holds the first argument for Intel 64-bit calling convention, and then puts the address of putchar into arrayx and jumps to arrayx, or calls it. It doesn't just jumps there, and that prints it, and at some point it will return, and we don't need to clean up anything since it was in the register. So yeah, that's good. The same for read, and the same and for begin. We actually have to patch the position. So we have to check that the current byte is 0. If it's 0, we just jump to some position which will be filled later. Otherwise, we proceed with the current machine code. And yeah, if we look at the end of the loop, again, we do the same. We test if the current byte is 0. And here is the actual calculation of the position. And yeah, and then it just patches the offset at the beginning of the loop with the address just behind the loop. And yeah, at the end, we just go out of the procedure and we just do a return. I was thinking about writing some DSL for some machine instructions, but yeah, I haven't got to that, and it is at this point. Okay. So, how much faster is it? Let's do cargo build. Release does not make any sense, does not change anything in this case, because the machine instructions that are actually executed are the same. And now we can do target debug, Brainfuck JIT compiler, and let's give it the program, and let's time it. Let's see. And that's what it takes when this is machine code. It was 35 seconds, and now it's 1.1 second. Okay, but now I'm trying to move myself from Intel to aarch64, and it's not exactly easy because okay, and let's try the same there. Yeah. So if we compile BFI, the interpreter, it works, but it is quite slow. So let's just try something simple, and yeah. Now let's try to time it. It will take quite a bit of time to interpret the Mandelbrot fractal. It's just a Raspberry Pi, and yeah, it takes quite a bit of time. Okay, while it's doing that, let's also try to compile the JIT compiler. Cargo build. And we see the compile error because yeah, this target architecture is of course it's not supported. Okay, so let's go back and let's try to make it happen. So what do we have here? It all starts with what? That was a submodule. Yeah, it all starts here. This is some ugly Rust code. It was one of my first Rust, non-trivial Rust programs, and yeah, it's pretty bad actually. Am I in NeoVim? Yeah, I am, but it's pretty old. Okay. Yeah, let's go to the lib. Let's go to the bf3.js. And now, what is wrong with it? Yeah, it's pretty old. This NeoVim is pretty old. Okay, so let's just fill in this one. aarch64. Let's say that we want to support aarch64 as well. Let's compile this. Let's copy this stub. Let's change this to aarch64. And let's put it here. So it took 150 seconds to draw the Mandelbrot fractal with the interpreter. Okay, let's remember that, and let's see if we actually see the error. Yeah, and now we are failing here. Good. So let's remove this thing, and let's think of how to actually map this to aarch64. So the first thing, I will need the data pointer, the data pointer register. I will need to determine which one will it be. Then What else do I need? Yeah, I think that's fine. Let's return here aarch64 convention. What's wrong with it? Why does it not show me aarch64? Let's just look at this. Okay, so there are 31 general purpose registers from x0 to x30, and x31 is SP, stack pointer. Okay, x0 to x7 used for parameter passing and return values, which is very straightforward. So we can have up to 8 arguments, or we read them from stack. x8 used as an indirect result location register. Okay, then we have temporary registers used as intra-procedure calls scratch registers, whatever that means. Yeah, x18 is reserved, x19, x28 callee saved registers. And I actually like that. I want to have a register which is which I don't bother to save. So what's frame pointer and link register? Okay. Stack alignment must be 16 bytes. This is important. Functions must maintain this alignment. Return values are in x0 and x1 if needed. Callee saved registers are these ones. So it sounds to me that we can use x20 as the data pointer register. Then, what does the prologue epilogue look like? So right now, my first task will be to just call an empty stub and successfully return from it without segfaulting. Empty stub and return from it without segfaulting. So what does it take to create an empty function stub on a aarch64? Okay, I will need a place to experiment, so let's create that, and let's create something like hello C, whatever, int main, should it be void? Yeah, whatever. And let's say it takes one parameter, and let's say it's int x, and let's call it with 42. Whatever. And now gcc hello C. Let's do some obj dump. Yeah, that's not what it should be. Oh, yeah, should have moved it there. Obj dump minus d out. And now let's take a look at our function. So yeah, what does it do? So first of all, it moves the stack pointer by 16 bytes down. so it subtracts 16 bytes from the stack pointer. Then it stores it stores what? Interesting. Why does it store the int that was passed on the stack? Then it does a no op, and then it adds 16 bytes to the stack pointer back, and then it returns. Well, so they do have a return command. Interesting. Okay. So, okay, let's just steal this and let's put it in our program. So, we have an executable memory, and now let's just emit. I don't have completion here, so yeah, it will be painful to write. Okay, that is not a problem. Okay, so let's just emit a prologue, function prologue, and this will be sub PSP stan, and this is encoded as D1. Oh, it's just 43 FF. Then I don't want to save it the argument on the stack. I know that it is in x0. Then let's just emit. Let's just put it back. The stack pointer, let's just put stack pointer back. Where did you go? And let's return. The return looks interesting. D6 5F 03 C0. Okay. Okay. Will we even run? And yeah, we didn't. Okay, now let's figure out why. So Rust LLDB, yeah, I think it's a good idea. Debug, FGC3. LLDB not found, please install it. No, okay. Maybe Rust GDB then. What was the command to set it? And now let's look at backtrace. Previous frame identical to this frame, corrupt stack. Oh wow, interesting. So what is the address of func? Oh, that's not what I'm debugging. Yeah, right. Okay. So, what did it say? It says that data memory is here and code memory is here. Let's try to debug that. So let's print what we symbol. Did I copy it? So that's where it puts the machine code. Let's look at it. That's true. And it looks like the endianness was wrong. So actually they should be the other way around. And this should be also like this. And I also have to swap these ones. This one goes here, this one goes here, and this one goes here. Yeah, I know it is not syntactically right. Yeah, okay, let's try again. And it actually returns without segfaulting. Okay, that's a good start. Okay, the first to do is done. Now, what can we do? Let's take a look at the Hello World program. And let's see. So first of all, we have some pluses, then we have a loop, then we move, then okay, yeah. So I think let's repeat what we had here. So x20 contains the address of the data memory, because it is passed when this JIT code is executed. So the data, no, it's in, okay, yeah, the data, the memory offset. The memory offset is passed in x0 as the first parameter of the function. Yeah, now we have to move it somewhere safe. Let's take a look at the argument, at the calling convention again. What I would like to have ideally, call these saved registers. Yes, I don't want print functions and get char functions to erase this data. Yeah. Okay, let's think how to do that. Okay, so there was a complaint about the sound. Is it better? I will try to tone it down a little bit and maybe it will get better. Oh, yeah, and maybe that will help as well. Please tell me. Okay, now. No, we need to actually save it somewhere safe, the memory offset, which we have. We need to initialize the data pointer register to 0, because it will be there at the start. Initialize to 0. Then save the memory address to a Kali saved register. Let's save it in x19. Why not? Okay, save the memory. Yeah. And now let's repeat the usual edit. And now move x. Okay, how do you move in aarch64? Okay, that sounds good. So the first one is the destination and the second one is the source. Now let's go into TMP. Let's assemble it. Test S. Yeah, I don't want to assemble it completely. Let's put it into test O and let's do objdump test O. Okay, so that gives us the code that does this. Exa emit mov x19 x0. And this is done like this. F3 03 00 AA. Initialize x20 to 0. Okay, how do you do that? Can you do literals? Maybe this will be actually helpful. Move. Okay, registers, bit manipulation, vector data, loads and stores. Oh, maybe this has the instructions that manipulate it as well. Interesting. Instruction set architecture. Should I look at their ARM reference? What's this? Okay, move. Move data, add. Store register. Maybe this is what I need. Interesting. Okay. How do I set it to 0? Can I XOR it? Yeah, maybe let's just XOR it. 64, XOR. Exclusive OR. That pretty much makes sense, yeah. It should be called exclusive OR, E or R, not X or R. Okay, let's see how it is encoded. And this will look like... So, the destination register is 20, and we XOR x20 with itself. Will that be enough as a shortcut? Yeah. x20. Okay, let's dump it back, and let's put this XOR here. So emit x20, x20, x20. So whatever was in it is XORed with itself, and it becomes 0, which is put back into x20. Maybe it's a very stupid way to do that, but yeah, it always takes 4 bytes, so why not? Okay, 0x94, 0, 2, 1, 4, and CA. And now I need to actually understand how to put a breakpoint and to verify that the registers are set the way I need. Okay. Let's do cargo build. Let's run Rust GDB. Oh yeah, I'm not in here. Rust GDB. Okay, let's put a breakpoint on what? Where do I actually call this function? soc lib and execute contents. Data memory is here, and then we get the entry and we jump into the entry. So that's line 79. So let's put a breakpoint at librs 78. And at this point we have already compiled the program, so the JIT memory is already filled with machine instructions, but we don't jump to it yet, so I can inspect it in GDB. Okay, now I have a breakpoint there, and let's run hello BF backtrace. Yeah, I'm at the right place, and let's examine the memory. And by memory I mean this one, code memory. Let's disassemble it. And let's print 10 instructions. So yeah, what do we have there? We have this prolog. Yep, sub is sp16, mov x0 to x19. We have exclusive or x20, which zeroes out the x20. Then add stack pointer. Why is it? Oh, it's the epilogue already. Okay, yeah. So now let's put the breakpoint at the epilogue. No. How do you put a breakpoint at an address? Yeah, this is the way you put a breakpoint on a bare pointer. Okay, and now let's continue. Backtrace. We are somewhere, we don't know where, because we are in the JIT code. And now let's examine the registers. What was that? Info registers, right? Yeah. So x20 should be 0 at this point, and x19 should be set to what was in x0. Okay, yeah. Actually, it's very simple, and I did not have to actually verify that, but I'm just trying to remember how to actually look at the registers in GDB. Yeah. So x20 is zeroed out. This is our data pointer. x19 points to data memory, and x0 can be erased by future print char, put char, get char, and so on and so on. Yeah. So that looks good. Yeah. Now let's continue. Yeah. What do we do next? Next, we actually have to start compiling the instructions. And this will be interesting. Yeah. For op in, we have operations passed. Oh, that's terrible Rust. Yeah, I really didn't know any Rust back then, because yeah, I should change it to to a slice. But yeah, I didn't know any better back then. Yeah, for now let's roll with just a vector of operations, with as a nonsensical reference to a vector of operations, which doesn't make any sense. Okay, let's iterate over it. Yep. Let's match operation on. What was that? Op add, right? Some number. To do whatever this is. Okay, and in case of add, what do we do? Yeah, actually move is even simpler to start with. Move by. Okay, now here we uncritically and without any bounds checking just change the data pointer stored in x20 by the literal that we receive here. So x20, basically like this. So what is this in terms of machine code? Oh, okay. TMP. Let's open our Scratchpad and let's. So what type is this by thing? I remember using iSize to store it. So on aarch64 this should be 64-bit signed integer. So how do you add add immediate? Yeah, that's what I need. Add immediate adds a register value and an optionally shifted immediate value and writes the result to the destination register. This instruction is used by the alias mov. Okay. On a 64-bit, you specify a destination register, a source register, what you want to add, and then the immediate. And you can also specify an optional shift, which is constant integer data size. What is the range? Immediate 12-bit immediate. So if we want to add more than a 12-bit, is it signed? Is it unsigned? Okay. Oh, one other thing that I can do is I can use a scratch register. I can load this immediate there, and then I can just add them. Yeah, that sounds pretty good. So I can actually use the scratch register, which will be, what are the scratch registers? Temporary x9. Yeah, I like X9. So, what I will be doing, mov X9 by the immediate, and then I will be doing mov, not mov, but add X, the data pointer register. I will add X9 to X20 itself. Yeah, and this is the shortcut form, if I remember correctly. Let's verify that. So, where is my scratchpad? Yeah. Yeah. The first thing is to load this immediate into a register. Can I actually just do it like this? And then I need to add X20, X9. I wonder what happens if this will be a negative number. Let's do that, why not? 16. Now let's assemble it again. Let's change it like this. Comma expected between operand operand X20. So it does need. So this shortcut is not acceptable. You still have to do it like this. Okay. Okay. Let's look at the object dump. Yeah. And now, what do I have? So the 12-bit immediate. I'm wondering if mov. How does it encode it actually? What is the part in here where the number is encoded? If I change it to 0, what will happen? Or maybe I can read documentation for once. Okay. I want to see the documentation for mov. Immediate. Oh, so S sign extends. Good. Does it take a 12-bit immediate? Yeah, I believe it does. And it puts it into... How do you read this? Is it encoded here? Ah, I see, I see. So it takes a word and uses the lowest 12 bits to store the immediate operand that you put in there. Okay, I see. So in this case, what would be the lowest 12 bits? 1. So I know that in memory this looks like E9 01 8092. Let's look here. So the highest 4 bits have a condition. I don't know what 9 means in this context. Then we should have 3 zeros, 3 0. What am I even looking at? What I can guess that this 9 should be the register encoding. Is this correct? Register destination. So what nibbles are there? There is one nibble here, there is one nibble here, there is one nibble here. Then we have a nibble with the register that encodes the register, the destination register. Then we should have 0. Okay, let's do a stupid thing. Let's just 0 it out and see what changes. 0. Let's repeat that and stomp minus d tmp test o. So what changes? D. Wow, it changes pretty drastically. Maybe I should use move signed. If I understand that S is signed, but no, it is not. If I change it to 8, what changes in this? So this one corresponds to the register. This nibble encodes the register. And if I look here, right, 0, 0, 0, 80, D2. And this is the register. Why? Yeah, I know, but I don't need. Yeah. I know that big numbers are not trivially encodable, but yeah, I just want to know how to encode this small 12-bit number. So I don't care about huge offsets right now. I can just insert a test that says that the number is too big and it's not supported. So where am I? BF3RS, yeah, here. And wait, I didn't even have a way to say that this compilation failed. Wow, my Rust was just truly horrible. Yeah, so I should say to do change ops to a slice of operations, and another to do signal that compilation failed, return result. Okay, but for now we can just bail here. Okay, if how do you say not in range? Okay, let's not complicate it. Python 3. Okay, a 12-bit number is this one, so it's 4096. Okay, minus 45 is if it's not true that by is less than 4090, or maybe let's put it in hexadecimal form. FFF and by FFF, then just how do you kill the Rust program? Oh, okay, panic. Yeah, panic. Only 12-bit. Shifts must fit in 12 bits. By is equal to by. Yeah, and because by is actually statically known, and you can definitely generate a file which has more than 4,000 pluses or moves sequentially, but I think it'll be okay to panic for now. Shifts must fit in, but by is equal to by. Okay, good. And where do we put these 12 bits actually? Add says immediate 0. What I don't like here is unsigned int. Is there a way to make it signed? 0 extend. Move 0, move, what's k? Whatever. Okay, chat, how do I assign extended? Okay, but immediate is an unsigned immediate in the range of 12 bits encoded in the immediate field. But this is add. Okay. How do you assign extend on aarch64? Assign extend. Yeah, yeah. Maybe it's just this, yeah. Add. Can you actually do add x20, x20? Then I have an immediate, for example, 0 and uxtb. Can I do it like this? Or minus minus 16? Does it work like this? Okay, yeah, I think so. Does it work like this? Only LSL shift is permitted. So what's uxtb? So I still have to put it in the scratch register. X9 minus 16 X9 uxtb. Okay. Let's do a jump one more time. Let's compile it and see what's changed. So here 9 is preserved. What's changed here? Yeah, I really don't understand what this encoding does. Yeah, there is another idea. Yeah, thanks. There is an idea to generate a sub or add depending on the buy. That makes sense, yeah. If buy is less than 0, generate sub x20 minus buy, else add x20 buy. That doesn't look too bad. And I believe sub will take a 12-bit immediate as well, right? aarch64 sub. What? Maybe this will be more helpful. Okay, so what does sub do? Okay, let's try that. So the scratch is here, and I'm back to the plan of using this and using a constant here. I also want to look at x20, for example, what is a recognizable number? 10. It will be a x28. Yeah, I want to see all of that. And maybe something like x20. Does it work this way? 5, 4, 6. And then I want the same with add, just to see the encoding part. And now let's look at this. Yeah. And now the last part doesn't change. So add is 91 here. Where does 5, 4, 6, 4, 5, 6 go? Where is it in here? 5. Yeah, maybe it's not a nibble that corresponds to a nibble here, because I don't really see it. Okay, but what changes? x20. Why does it change this? Okay, I thought it would be obvious where the immediate goes in here, but right now I'm a bit lost. Yeah, I really should read the encoding, the documentation about the encoding. Yeah, let's look at this. So this is something that that ends with 1. So yeah, right now I'm doing a very basic job of just decoding the instructions. And this is also 942200D1, and this is also 942A00D1, and this is 94 to A. Is it to A? 5A. Okay, that makes sense. 11D1. Here the command is 91. No, it's 9491. Two. Okay, bits 1022. Oh, that's why it's not obvious. Yeah, okay. If it starts at bit 10, then yeah, let's do a quick calculation. Let's move it by 10 bits, and let's move it to hex. that actually produces a 0, right? That was D1. Yeah, that was 0 in here. If I put 2294 in here, it's 8. Yeah, finally. Yeah. Thanks. So basically, I need to shift my immediate by 10 bits to the left, and then I need to OR it with a template which looks like this. And okay, perfect. Thanks. So what was D1? It was a sub, yeah. Yeah. And in this case, I need to emit. Did I have U32? I do. That's good. Actually, it's pretty good to have it instead of just writing it down every time as a slice. Okay, so this is the pattern that I have, and I need to put the immediate in there. And in order to do that, I need to OR it with minus by shifted by 10 bits. And the same for add, but the basic template is this one. Yep, and now I want to see this generated. In order to do that, so what do we have here? We have 8 pluses in here. Okay. I need to have moves. Okay. Yeah, let's just create this a test program for that. TMP test move pf, and let's say we have 8 moves right, and then we have 10 moves back to the left. And what we should see in the generated bytecode is sub x20 x20 add x20 x20 constant a, and sub constant not 9 8, and sub a constant 10. And if I go to my scratchpad, which is here exactly, yeah. Let's compile that and look at GCC and opt dump. Okay, so what I should see is 91002294, and for this I should see D100 to A 94. Okay. Oh, I mistyped 00. Yeah, 2294. Good. Now let's actually see that this machine code is generated. So, do I need to rebuild? Yeah, I do need to rebuild. Okay. Do I not have a move? What did I have? Oh, okay. It was called move, not to confuse it with any assembly, which makes sense. Okay, what do I have here? What's wrong with you? Mismatch types, expected eye size. Oh, okay. A bunch of small petty errors. Okay, that was fixed. No implementation for. Rust, why? Why do I have to think about this at all? What's next? Consider the reference date. Expected. Okay. Okay. Remember, you could do some pattern matching by ranges, but I don't want it to go into there yet. Okay, and now can I just dereference it here? How do I do that? Okay, can I do the reference here? Cargo build, expected pattern, yeah. Oh, move. Yeah, I agree. It's called move with E. Now, expected eye size found whatever. Okay, let's just do some shadowing. Where am I? My network is being slow. Okay. Let's get rid of that. Let's say that bar is equal to dereference in bar because I don't know Rust. Let's try cargo build. Expected U32 found U size. Good. Okay, and I can actually say that this is I32. Oh, expected U32 found I32 in. Okay, I see. Okay. Okay. So in here, I get a reference to eye size. I need to generate a U32 in the end. I also either have to use add with overflow, or I have to carefully check that this addition makes sense. Okay. Yeah. So I have a nice size. Why is my network so slow? So I have a nice size. I can convert it to, I can truncate it to ICE32, and I can just bit change it to U32. Will negative number be converted to U32 representation? Okay. Yep. let's say that n whatever is equal to minus by as u32. And here let's say that n is equal to by as u32. And that should be good enough. Let's try that. You can convert an i32 to a u32 and panic is the converted value. Doesn't fit. Try into unwrap. Oh, Rust. Okay. So, emit u32. Is the result not a u32? Okay, I don't have time for this. Yeah, let's just do what it says. Obey the compiler. Try into, unwrap, whatever. I just want to see my bytes in memory. Yep. I don't need this. I need cargo. Cargo build. The following trait is implemented, but not its scope. Perhaps add a use for it. Why is that? Was it I32? What is happening here? So the memory is defined in JIT here, and it takes a u32, which makes perfect sense. But somehow it doesn't work here. Okay. Whatever. Convert, try into. Okay, cargo build again. Now what? Rust. I32 found in the scope. Oh. Maybe. Why is it I32? Because the type of by is u32. Oh, I'm spending a lot of time on something very basic in here. Where was I? Where is my BF3? Okay, so what's wrong with this code? Is it not u32? Oh, right. And then I think I will not need this. Yeah. Oh, will it be it? And this stupid convert goes away, right? But I added it to another file. Okay, whatever. Okay, now let's try to run it. So we have Rust GDB. Let's put a breakpoint on what? 78, was it? Uh, 78, not 718. 78, yeah. Yeah, that's correct. Let's run it. Let's wait, what? Oh, I didn't specify any arguments. Let's run it with tmp mov bf. We are at the breakpoint. Let's look at the code memory. What was that command? Was it this one? Yeah, I think so. So now, what does it generate? It generates nothing. Interesting. So why does it not work? So this should translate into add x20 x20 8. This should translate into sub x20 x20 10. But I don't really see this. Okay. Think I'm missing something obvious again. Yeah, maybe. Okay, let's just say let's just try this. I need to convert it, right? Okay. And here I need to take the bits. Oh, yeah, maybe. Yeah. Maybe it's optimized now. Yes. But why? Did I do compression somewhere? Oh, compiler. Yeah, let's look at the compiler. Yeah, correct. There may be repeated commands. So I do change a sequence of op-ed into one op-ed. Okay, that makes sense. Good. So what do we have here? X20 is moved left by 2. Okay, my compiler is smarter than me, which is a good thing. This is basically the goal of a compiler writer, for the compiler to be smarter than the compiler writer. I like this. Okay, and yeah, I will have to stop the stream at this point. Okay, see you at the next stream. And I can see that I have implemented 2 of 8 brainfuck commands at this point. And see you in the next stream.